Hello and welcome everyone, both those that are tuning in person and those that are tuning in virtually. This is day 3 of the Supercomputing Asia 2022 conference, and this is the industry track. So for those that are tuning in person, please tune in to channel number 5, so you will hear the audio. And those that are tuning in virtually, just enjoy. We have a very interesting lineup of talks this afternoon, and let's kick it off with Mr. David Slama, Senior Director at NVIDIA, with the title of his talk, Cloud Native Supercomputing. Mr. Slama, please.
Cloud-native supercomputing blends the power of high-performance computing with more offloading capabilities and acceleration capabilities, and with the security and ease of use of cloud computing services. The NVIDIA Cloud-native supercomputing platform leverages the NVIDIA Bluefield Data Processing Unit, the DPU, architecture with several advantages. High-speed, low-latency NVIDIA Quantum Infiniband networking to deliver bare metal performance. Second, secured infrastructure for data protection and tenant isolation. Third, data storage for tenant workloads. And the last one, software-defined infrastructure based on Docker for infrastructure and tenant services. Cloud-native supercomputing is an infrastructure for on-demand high-performance computing for HPC and AI services, simply and securely. In the traditional supercomputing, we offered bare metal performance for cloud IT managers without any isolation and secured infrastructure. Cloud-native supercomputing is offering a flexible secured infrastructure for multi-tenancy and offloading and acceleration capabilities. Cloud service providers can run and deploy multi-services as Kubernetes pods on top of the DPU per tenant request or for infrastructure advantages such as telemetry, security, resource allocation, and others. From offloading perspective, cloud-native supercomputing can offer several advantages. Acceleration and offloading of HPC communication on NVIDIA DPU. For example, UCC collective offload service on the DPU or UCX offload acceleration service on the DPU. More advantages are active messages, smart MPI progression, data compression on DPU, and of course user-defined algorithms based on Docker API. From security and isolation perspective, cloud-native supercomputing provides zero-trust architecture with security services such as host attestation, host introspection, and more. Storage virtualization for a remote storage allocation. Tenant SLA, for example, rate limiting, bandwidth guarantee, and reservation of network resources based on tenant isolation and picky detection. In this slide, we can see two types of services. On the top in gray, we can see the tenant services for acceleration and offloading capabilities. Below in green, we can see the infrastructure services for telemetry, security, remote resources allocation, and isolation. Both types of services should be managed and controlled by the sysadmin or the cloud provider according to their needs or per tenant SLA or requests. On top of the bare metal servers, tenant can deploy and run their workloads and applications as Kubernetes containers. Today, NVIDIA is offering 3 Cni plugins for Infiniband. The first Cni plugin is the SRIOV mode. In order to use a container, IT manager should create virtual functions, and each container should be mapped to a virtual function. With this Cni, we can define quality of services parameters and isolate virtual functions. The second Cni plugin is the shared mode. In this Cni, IT managers can create containers without any limitation on the bare metal machine, without any isolation or tenant SLA. The third Cni plugin is the host device mode. In this mode, the number of containers are limited to the number of the physical ports. Each container mapped to a dedicated physical port, and in this option, isolation and SLA are available. In cloud-native supercomputing, we are using mostly the second option, shared mode. The reason: secured infrastructure that isolate and allocate bare metal resources to a tenant who would like to run his workload and application as container on his x86 bare metal server without any limitation or isolation. Cloud-native supercomputing creates two zones. The first zone on the top in gray is the bare metal server zone that provided to the tenant by the cloud admin and controlled by the tenant. The second zone below in green is the DPU zone, which controlled by the IT manager, the cloud manager, or the cloud provider. In the bare metal zone, we can see in gray two major planes. The first is the tenant plane. The second is the user plane. For example, Coca-Cola is the tenant, and Coke Diet and Coca-Cola Cherry are the users under the same tenant. The tenants get bare metal allocations from the provider and can decide which applications or workloads to run and if to use any external tools for managing jobs between the users. For example, Slama or Kubernetes, as we can see here on the top gray area. In the DPU zone, we can see in green two major planes, the infrastructure plane and the provider plane. The infrastructure plane is providing the network infrastructure and the facilities to the providers. For example, an external network for internet connectivity with security and isolation for tenants, or connectivity to a remote storage. The provider plane is responsible for all the dynamic allocations for infrastructure and tenant needs. For example, peaky isolation, remote storage allocation, such as logical volume or a file system, telemetry and server cleanup between different tenants. In this slide, we are showing how we can use Infiniband network for all cloud activities. We are using it for the compute plane, the storage plane, and user management plane. In each compute node, we can use one or more DPUs. For the Infiniband management and orchestration capabilities, we are using UFM in high availability mode. UFM is covering two critical aspects of this solution. It provides full backup and high availability for all the critical services in the network, for example, Subnet Manager, Aggregation Manager of SHARP, and UFM telemetry. It also exposes the SDN and Cloud API for integration with third-party tools. By using UFM, cloud service providers can integrate their own software platforms to UFM or use open source projects such as Openstack Kubernetes, or Slama. In order to build our first blueprint for cloud-native supercomputing, we use three components. On the left, the NVIDIA DPU Manager for DPU provisioning. The second component is the UFM to manage the Infiniband cluster and to isolate resources between tenants. The last component is Openstack for bare metal cloud provisioning and tenant lifecycle management. UFM offers a rich, comprehensive northbound REST API for integration and automation. By using this API, customers and partners can build their own integration with any third-party software. NVIDIA is offering several plugins and examples for customers. For example, Kubernetes Cni Plugin, OpenStack ML2 plugin, Slama plugin, and LSF plugin. All these cloud and job scheduler plugins developed by NVIDIA and interact with NVIDIA UFM Enterprise REST API. In this OpenStack example, we can see how NVIDIA ML2 SDN plugin is interacting with UFM REST API to create a tenant and isolate it from other tenant resources by using the Cloud API. How it works. The SDN ML2 plugin uses two main operations for this. The create a new network post operation and the add port to existing network post operation. With these two operations, UFM created a network and assigned the given ports to this network, but also isolated these resources from the rest of the resources in the network. Picky isolation is limiting the traffic to a tenant scope and blocking any traffic between tenant 1 to tenant 2, for example. In this slide, we are presenting 15 nodes isolated by OpenStack and UFM integration to 5 tenants in 5 different pickeys. By using picky isolation, each node in the cluster can interact with UFM node but cannot interact with other tenant resources. While creating a new tenant, OpenStack ML2 plugin sends a notification to UFM REST API. UFM reserves and isolates the ports on the bare metal resources only to the selected tenant. Once the tenant lifecycle is completed, UFM received another notification from the SDN ML2 plugin. In this case, UFM removes the tenant picky and releases the resources by using the following API of delete operations. With this ML2 plugin and UFM integration, we are getting network provisioning per tenant, full isolation between tenants, allocate network resources per tenants, and of course tenant SLA based on picky isolation, such as rate limiting, bandwidth guarantee, and sharp resources allocation. Today, the DPU Manager offers capabilities for DPU provisioning. Soon, we will support also DPU lifecycle management capabilities, services deployment capabilities, and services lifecycle management capabilities. All these capabilities will be exposed over the DPU provisioning API, and it will be very easily to integrate any third-party tools into our DPU Manager provisioning API. The current software solution of NVIDIA DPU provisioning uses a customized version of NDO based on Ansible. As we can see here, we added 7 new Ansible playbooks and modified 3 of them to support our needs for cloud-native supercomputing. The main reason for this change was the fact that NDO controls the DPU but also controls the x86 server, and in our case, Ironic should control the bare metal server. Here we can zoom in and see the logical connectivity of the compute nodes. The platform BMC 1 gig interface is connected to OpenStack Ironic controller and also to the DPU manager. We are using this network for boot cycles and provisioning of the bare metal machine. The 1 gig interface on the DPU is connected to the DPU manager for DPU provisioning. On the top, we can see that the network port is connected to the Infiniband cluster for compute and storage network. In this solution, everything is done over Infiniband, and only the DPU provisioning and the bare metal machine provisioning is over 1 gig interfaces. For the next step, we are planning to deploy Kubernetes in 2 levels, one for DPU services and the second for application and workloads of tenants on top of the x86.
Thank you, Dudu. In the following session, we will demonstrate a step-by-step deployment flow of DPU-enabled x86 servers over Infiniband Fabric for cloud-native workloads using OpenStack and DPU Manager orchestration tools. Please keep in mind that the presented solution is only one example on how to build and deploy a cloud-native supercomputers with DPUs, and we introduce it as a reference so anyone can take it and build its own solution with those or other building blocks. Let's start with a short overview of the building blocks used for this reference solution. As a cloud service orchestration, we use OpenStack, the most widely deployed open source cloud operating system. We will use it to orchestrate and provision our entire secured multi-tenant supercomputer cloud. As bare metal provisioning platform, we use OpenStack Ironic to introspect, clean, and provision x86 bare metal servers for the cloud tenants. To provision the Infiniband fabric, we use NVIDIA UFM, which is fully integrated with OpenStack networking platform Neutron using ML2 mechanism driver. This integration allows us to seamlessly provision tenant networks over Infiniband fabric. And for DPU provisioning, we use the DPU Manager NDO, which is a set of tools and services such as Foreman, Ansible, and AWX, allowing us to deploy and configure NVIDIA Bluefield DPUs at scale as part of our cloud-native supercomputer. Let me introduce the components and networks involved in the current design. You can see here several nodes with different roles, such as OpenStack Undercloud node, which is the node deploying the OpenStack overcloud controllers, the UFM Fabric Management node, which is the one responsible for talking with OpenStack Neutron service and provision the Infiniband fabric. Next to it, the OpenStack overcloud nodes, which are the controllers used by the cloud admin tenants to orchestrate the bare metal services. We also have there the bare metal x86 tenant nodes with the Bluefield DPUs, and the DPU Manager node, the NDO, which will be deploying and provisioning the DPUs. Let's talk about the networks. The first one, the Undercloud Provisioning Network, is an Ethernet network used by the Undercloud to pixie boot and deploy the overcloud controller nodes and to access it for management operation. In addition, this network is used for the API communication between OpenStack Neutron and UFM Fabric Manager. The IPMI network is used by the Undercloud to run IPMI operations against the overcloud nodes. It is also used by the overcloud Ironic service to run IPMI operation against the bare metal tenant servers, and in addition by the DPU Manager to run IPMI operations against the same servers when it's required as part of the DPU provisioning. The external network is an Ethernet network providing internet connectivity to every component except for the bare metal nodes and the DPUs. The DPUs will use NDO as a gateway for their internet traffic, while the bare metal servers will go over Infiniband fabric to a virtual router instance located on the Openstack controllers, and from there to the external Ethernet network. The Infiniband network is a high-speed, low-latency fabric which is used for multiple networks separated by PKIs. Openstack Control Network, Tenant Node Provisioning Network, Storage Network, and Tenant Networks for supercomputing data workloads. And the last network in this diagram is an Ethernet network used by the DPU manager to deploy, provision, and manage the Bluefield DPUs, which are connected to this network over its out-of-band interface. Before we can proceed with the demo, there are several basic steps we need to take in order to prepare the setup. First, we need to install the OpenStack Undercloud node, then the DPU Manager node. Next, we will need to install the UFM Fabric Management node and generate an API access token. And finally, we will inject this token into OpenStack deployment configuration files and deploy the overcloud nodes. Once we perform those steps, we are ready to start with the demo. Our demo deployment flow will include two main phases. The first phase will be done by the DPU Manager platform, the enrollment and provisioning of the DPUs. In this part, we will prepare an inventory of the deployed DPUs, trigger a PXE deployment of the DPU's operating system, and execute multiple DPU Manager playbooks to configure and upgrade the DPUs. The second phase will be done by OpenStack platform, the enrollment and provisioning of the bare metal nodes. Here, we'll prepare an inventory of the deployed servers, create tenant virtual networks and see how they are automatically translated into Infiniband fabric configuration by UFM, and finally, we'll create and deploy a couple of bare metal instances over this Infiniband fabric and test IP over IP connectivity. Okay, we are ready. Let's see the demo. Okay, our starting point is the DPU manager, the NDO. We start by creating an inventory file with the DPU details. This is a basic Ansible inventory file used by NDO to deploy and configure the DPUs. Once the file is ready, we can go ahead and run our first Ansible playbook for creating the DPU host objects inside NDO's Foreman engine. The Foreman component, which is part of the DPU Manager toolset, will provision the OS on the DPUs in few moments. We can see in its UI the DPUs being added to the inventory after we executed the playbook. And as we can see, if we go inside one of the objects, it is in pending installation state, which is ready for PXE deployment. Next, we will run a playbook for setting PXE as the first boot option for all DPUs in our inventory. And finally, we issue a server reset playbook to trigger DPU initialization and PXE deployment. Let's follow one of the DPU's console to see the PXE boot process in action. Few minutes fast forward and the DPU OS is up and running. Now it's time to complete some DPU configurations in order to tune it to our cloud-native supercomputing deployment. This playbook will collect the server port GUIDs, which are required for the OpenStack bare metal deployment in the upcoming steps. And this playbook, on the other hand, will set the port PXE Infiniband PKI ID according to what it is specified in the inventory file. In this case, we used PKID 70 to match the PK we will use later on for Openstack Infiniband provisioning network. This playbook will set the DPU's port link type to Infiniband instead of Ethernet. And finally, a playbook which will update the DPU's firmware to the latest release and issue a power cycle in order to apply the new firmware and the rest of the firmware parameters we modified in previous steps. I showed you the deployment playbooks executed manually one by one. However, it is also possible to log into AWX platform, which is also part of the DPU Manager toolset, and easily set a full playbook workflow to automate the required job pipeline. For example, we can start our workflow with the boot order playbook, add some more playbooks according to the order we want to run it, and execute it as a single job. Okay, we can now proceed with part 2, the OpenStack orchestration. As you can see, I already imported 2 server nodes into OpenStack Ironic bare metal provisioning using enroll node option. This is the place I also used the port GUIDs I collected previously. The GUIDs were used by OpenStack Ironic to pixie boot and provision the x86 servers over a dedicated provisioning Infiniband network, if you remember PKID 70 I was talking about earlier, while cleaning and preparing the server for tenant usage. Now it's time to create a tenant network. We will create a virtual VLAN network over the Infiniband fabric. As a physical network, we will select the one we specified in OpenStack configuration as the Infiniband fabric FISNet. The VLAN ID, 101 in this case, will be later on mapped to a tenant dedicated IBP key by UFM. To complete network creation, we will add a subnet information, DNS name servers, and that's it. We can see that once we created the network, DHCP virtual ports were created on the controller nodes. Those are DHCP server instances using IP over IB infrastructure to allocate IP addresses to the tenant instances. Let's switch to the UFM UI to see what is going on there. Under the Manage Elements, there are several Infiniband partition keys, or PKeys. PKey is a unique ID of an Infiniband partition, reminding in some fashion the VLAN isolation concept in Ethernet. The PKeys you see here were already created previously as part of OpenStack infrastructure. Now, let's see the magic happens. When we created the OpenStack network a few moments ago, Neutron sent, using the ML2 mechanism driver integration, an API call to the UFM, requesting it to create a tenant dedicated PKey and add the controller's DHCP ports GUIDs into the tenant PKey. When we refresh the page, we can see the tenant VLAN 101 was mapped to tenant PKey 65. And we can see the controller GUIDs are automatically added by UFM into this PK. And last, we will now create a bare metal instances using Openstack orchestration. First, instance name. Now the image we want to use as a guest OS image. Bare metal flavor. Our Infiniband tenant network. And that's it. Let's launch another instance. Again, instance name, the guest OS image, flavor, and the same tenant network as the first instance. Let me fast forward instance creation time. And that's it. Both bare metal instances are now up and running, both attached to the same Infiniband tenant network. Back to the UFM. Let's take a look on the jobs list created by the API calls received from OpenStack Neutron while creating the instances. As before, we can see an API calls were received to add the bare metal server ports GUIDs into the tenant PK, allowing it a full IP over IP connectivity with the controllers on the same tenant PK, in order to fetch an IP using DHCP and boot over this dedicated IB network. Now that servers are up and running and the network is fully provisioned, we will be able to test connectivity between the servers over the tenant Infiniband network. We can log into one of the servers, see its Infiniband interface and the IP that was allocated, and ping the second server over the Infiniband network. Thank you, and I hope you enjoyed the demo.
Thank you, Mr. Slama, for your insightful talk. I'm really happy that open source technologies are used to solve this big problem with cloud native supercomputing. Moving forward, our next talk is by Mr. Sean Petkovic, Principal Solutions Architect, APAC Netapp, and the title of his talk is Data Management for Quantum Classical Hybrid Multi-Cloud Infrastructure. Mr. Petkovic, please go ahead.
Hello and welcome to Data Management for Hybrid Multi-Cloud Infrastructure. My name is Sean Petkovic. I'm a Principal Solutions Architect on APAC Solutions Engineering Team at Netapp. My agenda today consists of 3 sections. Only in the first section we'll be talking about storage hardware. In the second one we'll be talking about storage management, data management monitoring, replication, caching. And in the third one we'll talk about a novel Netapp solution focused at AI and ML related to compute resource management in the public cloud. Section 1, data sharing for HPC, AI, ML, and big data. In recent quarters, we've been hearing from customers that although high performance and near real-time or real-time prediction from AI stacks and workloads is important, it is even more important to address certain other high priority requirements and challenges. Number 1, data security. Whether it's on premises or in the cloud, data has to be secure, and this awareness has been spreading to HPC environments as well. Data protection in the form not only from malware or leaks, but also the ability to recover your data, to copy in the cloud or maybe from a snapshot is also very important. Cloud integrations are ways to make your data accessible to the cloud or in the cloud for short-term bursty workloads or certain technologies or integrations that may not be available on premises. Before you can copy data to the cloud, sometimes you may also need to make sure the data is compliant and deal with violations of governance or laws and regulations. When you operate in the cloud, you will also find that the cost tends to go up really quickly if it's not properly optimized. HPC customers are also seeing advantages in integrating ML and AI stacks with their HPC stacks to avoid silos. And when all that is in place, there's still a need to do chargeback, showback, and perform continuous optimization of both performance and cost. As you can imagine, satisfying all these requirements and meeting all these challenges at scale, both AI and HPC requires a portfolio of solutions. Not only because of the features, but also because this processing happens in different locations. As the data authority on hybrid cloud, Netapp delivers AI solutions that remove bottlenecks wherever they may be, at the edge, core, or in the cloud. These solutions enable more efficient data collection, secure transfer, replication, acceleration of AI and HPC workloads, and a smooth cloud integration while satisfying your internal and external compliance and regulatory requirements. As you can imagine, at the edge is something that we would satisfy with a virtual-based solution such as Netapp ONTAP Select. We would securely transfer data to the core, to either storage grid or ONTAP. There, we would run heaviest workloads for training against EF series or ONTAP-based systems. We would then move some of the data to storage grid for data lake or long-term archiving. And when needed, we would burst to collocations or any of the major hyperscalers where we could still use our ONTAP-based cloud-native storage. This unique ability has not gone unnoticed by the analyst community. Netapp is the leader in block and file storage per both Gartner and IDC. As indicated earlier, Netapp has two hardware platforms that can be used for HPC and AI on premises. The first one is generally focused on AI. It provides scale-out NFS access to data. It is based on Ethernet and uses ONTAP appliances. It is a perfect solution for general-purpose AI training and big data analytics. It can serve medium to large number of concurrent workloads, and when you have competing workloads and different users, this system makes storage management and QoS management a breeze. It also provides excellent integrations for hybrid multi-cloud environments. The second system tends to be used in HPC environments. It provides a shared parallel file system, and the transport used for data is Infiniband. Storage platform that we use here is Netapp E-Series. You will commonly see these in HPC or employed for large AI workloads, such as NLP with Chinese, Japanese, and Korean language. Also common to these environments is that there is usually a low to medium number of workloads and users because the workloads themselves are quite significant. Let's take a look at the first solution, ONTAP AI, which we developed with NVIDIA. The challenges that this solution solves are as follows. Number one, customers are seeking to reduce risk of buying and deploying these solutions. This solution is flexible, it is validated, it is delivered with the right performance and scalability, and it makes it very easy for users to start right away, quick deployment, and deliver and build integrated data pipelines in no time. It also lets you unify AI workloads because it can run a variety of workloads really well, and it can also perfectly integrate with hybrid cloud and near cloud environments. When it comes to extreme HPC, AI, and ML workloads, whether it's in financial services, manufacturing, medical research, media and entertainment, oil and gas, or academic computing, Netapp offers integrated solutions with leading HPC file systems, including BeeGFS from ThinkPark and Spectrum Scale from IBM. In the case of BeeGFS specifically, Netapp is a diamond partner offering enterprise licensing and support to its customers. So in the case you want an E-Series based solutions for any of these verticals to get highest levels of performance and get deployment and support from a single source, we can provide that with E-Series and BeeGFS. This example is a little bit more detailed because it involves asymmetric design. As you can see on the left, we have a metadata management server connected to an EF600. This server or pair of servers takes care of file system metadata. On the right-hand side, we have a data storage block. This block has two storage servers connected to a single EF600. They work in an Azure pair, and your data is stored a single copy on EF600. It is all connected by Infiniband. Now, this block on the right is what you would scale out to get tens and hundreds of gigabytes in performance when necessary. Since last year, BeeGFS has added GPU Direct Storage GDS support, and this is also supported on solutions delivered on top of E-Series. If you're interested in more details, please search for NVA-1156. This slide shows some highlights from NVA 1156 with FIO and MLPerf performance with NVIDIA DGX A100 and E-Series EF600. On the left, you can see FIO results. With 8 systems, we're able to get around 55 gigabytes per second read bandwidth and peak scaling up to 65.7 gigabytes per second for 8 NVIDIA DGX A100 nodes. On the right-hand side, the figures are too small, but you can find more in the PDF document quoted. MLPerf training version 0.7 ResNet 50 benchmark test achieved over 150,000 images per second. These results are continuously improved on, and please look forward to updates coming in coming weeks and months. Another interesting development from Netapp in terms of this integration with BeeGFS is that we brought Kubernetes support to BeeGFS by creating a container storage interface driver, CSI driver for BeeGFS. This driver is open source. It is available to anyone. You don't necessarily need to have EF series storage, but as mentioned in the previous slide, if you do get BeeGFS E-Series stack, you will also get support for this as well for the rest of the stack in the storage system. These drivers enables two primary use cases for storage in Kubernetes. One is dynamic provisioning, which allows users to request storage on demand without worrying storage semantics. How do I create a file system? How do I use this command? None of that needs to be considered. You just use the regular way that you would use with Kubernetes. Another way you can use it is static provisioning. You can provide concurrent access to common data sets stored in a central location for efficiency. So that is required all the time. So normally you will really not need to provide this on an on-demand basis. And the entire stack of BeeGFS with CSI and E-Series can be provisioned with our Netapp E-Series BeeGFS collection for Red Hat Ansible. Object storage is usually an implementation of the AWS S3 API, and on premises it is often used in HPC, not for tier 0, tier 1, but sometimes as data lake, archiving, or other purposes that are extremely relevant in both AI and HPC. It can also be used to make access from the cloud to on-premises data easy, convenient, and secure. In that area, Netapp has a product called Storage Grid, and if you're interested in various designs that storage grid can be used with, please take a look at TR-4851. Section 2, Data Management and Monitoring in Hybrid Multi-Cloud. Now that we got our platforms and designs on-premises sorted out, and we want to exploit hybrid cloud, near cloud, or other combinations, we want to take a look at how we can best manage this data with Netapp Data Fabric. First, let's take a step back and take a look at key Netapp AI software solutions for individual systems or clusters. In AI, normally we would have a control plane that would be based off of popular open source solutions such as Kubeflow or Apache Airflow. Those would run in Kubernetes, and Trident, which is our CSI driver for ONTAP, or BeeGFS, CSI driver for BeeGFS, would be used to manage and provision storage. On top of that, to help data scientists integrate their workflows with storage, we created Netapp DataOps Toolkit. This toolkit simplifies AI data management, whether it's traditional environments or Kubernetes environments. It lets data scientists focus on the science rather than on IT and storage management. With it, they can easily include automation for snapshots, clones, and various other operations in their Jupyter-based workspaces or other workflows. So with this, we can deliver a full stack end-to-end AI workload management for single clusters. Let's take a look at some features and benefits of the Netapp DataOps Toolkit. As mentioned earlier, a lot more customers these days tell us that they get much better increases in speed of processing and operations by using their storage and storage features smarter. So one of these benefits is the increase of speed that you can observe when creating clones within seconds rather than waiting data to copy. Even if it's quick, it will always be slower than smart snapshots and clones that we can get in an ONTAP AI system. Secondly, they can quickly mount these volumes within Jupyter Notebook. It is also MLOps ready. It integrates into the entire Netapp AI control plane and can grow and scale with your needs. It provides speedy access to data without involving storage administrators, and you can always get easy access to current data. The other thing is you don't have to necessarily import and delete data for processing, because with the many thin clones and space-efficient clones, you can get data that stays on the servers, is accessible at all times, so there is no need to wait for data to be downloaded or copied from elsewhere. The ability to create many clones also makes it easy to get perfect traceability of experiments. You can retain hundreds of clones and create snapshots of the used data in combination with the code that you run your experiments with. Last but not least, it is also an enterprise-ready integration which facilitates teamwork with IT operation and provides cost benefits because storage capacity is used effectively and smartly. In a Kubernetes environment, on the left-hand side, you can see what is possible today with BeeGFS and Trident CSI. You can create new Jupyter Lab workspaces, delete them, create volumes, and delete volumes. On the right-hand side, with Trident only, meaning Trident with ONTAP, you can also clone Jupyter Lab workspaces, create snapshots, delete snapshots, and clone volumes very easily. In a traditional environment, we have recently also added two features related to S3. So you can pull content from S3 onto your NFS or BeeGFS, or you can push files back to S3. This comes very handy both on premises, also when you talk about the edge to core replication, but then finally also in a hybrid cloud or public cloud environment, because with this I can easily integrate my on-premises storage grid into my hybrid cloud workflows. We've just seen how easy and convenient it is to use the Netapp DataOps Toolkit to manage individual clusters. But what if we need to make our data available to remote clients or maybe use it in the cloud or near the cloud? This slide, although it's a little bit busy, shows several scenarios that you may consider in your data workflows. Before we begin, I want to point out that these gray rectangles represent hyperscalers, and these circles in them represent ONTAP-based native solutions offered by hyperscalers. Scenarios that I want to show today are 4 and show how we can take advantage of caching as well as replication for making data available remote site as well as migration. In the first instance, ONTAP Flex Cache is an ONTAP feature that provides read cache for ONTAP backend. Now, this backend doesn't necessarily have to be in the cloud. It can be another site. It can be in reverse. In reverse, for example, you could have AI deep learning workloads that read data from Flex Cache, but data at rest is not saved in the cloud, so you don't have compliance worries. The second use case is Netapp Xcp. There are two sub-use cases here. One is when you want to replicate data from legacy systems to a faster and newer ONTAP system for processing. This doesn't have to be ONTAP, it can also be StorageGrid or BeeGFS with E-Series. The other use case is when you want to replicate everything and then shut down. XCP is really great at migrating petabytes of data and hundreds of millions of files extremely quickly. It is a free offering. The third use case is Cloudsync, which I have here and right here. As you can see, it can be used almost for any-to-any replication. So when you have disparate sources, different clouds, and you want to synchronize files, consider Cloudsync. The last use case is also about caching, same as the first one, but what is different here is while the backend is the same, so it has to be ONTAP, Global File Cache is running a software application in Windows virtual machines. It is focused on SMB clients. It provides global read and write caching as well as global locking. So if you have heavily SMB dependent workflows, maybe related to genomics or something like this, you can consider Global File Cache. While we can copy data to the cloud, we also need to make sure that our data is secure. In December of 2021, Netapp has received NSA CSFC validation for security and encryption. While not all our customers have top secret data, it is useful to know that you can take advantage of the highly secure ONTAP storage platform to store your data confidently and reliably, whether it's on premises or in the cloud. This can save you time by making it easier to buy a pre-approved solution and avoid having to validate storage platform in each individual hyperscaler separately. It also limits the number of processes required to move or store data securely. It offers cost savings via reduced monitoring and simplified audits. While it is great to know that ONTAP storage platform provides excellent encryption and data protection, sometimes our problem is or challenge is that data cannot be copied to the cloud in the first place, so it cannot be stored at rest on cloud-based storage. In that case, you need to find out whether you may or may not copy it that way. In order to address this challenge, we have a product called Netapp Cloud Datasets, which can, even from the cloud, scan and categorize your data on premises, but also in any major public cloud. With that, you can identify PII before you copy your data in the cloud. You can gain visibility into your data, automate many routine tasks and policies, and secure data in a more systematic manner. Datasets can also give you alerts on high-risk data present on the system, such as credit card numbers, for example. So with this, you can confidently move and copy your data to the cloud on any ONTAP system, although we can also support other third-party systems, such as Amazon S3 buckets and OneDrive shares. In some other cases, you will also need to retain logs and forensics in the case of data breach or access auditing. Netapp Cloud Insights provide exactly that feature, and it uses F-policy from ONTAP systems to record all activity on file shares. It can cut and slice data activity by user, time, activity type, and file attributes. It can also generate user data access audit reports. You can see one example on the right-hand side. It can conduct data breach and security incident investigations or help you conduct them, and it retains historical data for 13 months. It also has an option in the premium edition related to automated responses to ransomware attacks. What happens is when a ransomware attack is suspected, administrators receive an alert to investigate suspicious activity. Cloud Insights can also, through these cloud secure features, take a snapshot to protect your data when a potential attack is detected. User can also be stopped, and user access can be restricted to stop the attack. So all these features, you can see one attack policy on the right-hand side, can be designed to fit your exact requirements. Section 3, Compute Resource Management in the Public Cloud. In this section, we'll examine how once we copy data to the public cloud, Netapp can also help you optimize your compute resource management with spot-based services. As some of you may know, public cloud environments include reserved instances, which are heavily discounted, on-demand instances, which are more expensive, and spot instances, which are also heavily discounted up to 90%, but can be terminated at a very short notice, which tends to interfere with Spark workloads. Spot Ocean for Apache Spark helps you take advantage of spot instances by auto-scaling your Kubernetes cluster running Spark. It can optimize instances based on the spot market by getting the best instance type in required availability zone for your workloads. Unlike manual taking advantage of Spark instances, Spark-aware auto-scaling can dynamically scale up and down based on the load, and it can gracefully handle spot kills and node shutdown. So when your spot instance is terminated, your workload can keep running. Last but not least, on repeated runs, optimization can be also based or start with historical workload characteristics. So we can optimize container sizes, we can optimize number of executors and partitions, shuffle tuning, and apply appropriate or effective feature flags that work well for your workload. We achieve all that with a simple interface called Spot Console, which shows all the relevant optimization statistics and data, including spending, I/O, and so on and so forth. To the user, they can still use Apache Spark the same way they would use on-premises, the same REST API, Apache Airflow, Jupyter, and other Spark integrations. Spot takes care of Spark-centric monitoring, right-sizing, configuration, and tuning. Like I said, all of that is available in the console. If you're interested in more details around this kind of optimization and workloads in the cloud, please check the datamechanics.co blog about a success story involving a customer who moved from 0 to production in 3 weeks, later 2020. The workload in question is Airflow Schedule ETL Spark pipelines processing terabytes of data on S3. So in this case, you could read data off S3 in AWS, but you could also read it off StorageGRID on-premises. Customer-facing data is presented to Spark-powered customer-facing real-time dashboard running Thrift JDBC server. Docker simplifies software dependencies, and the solution was less than 60% expensive than the next best solution that customer has considered. Before we wrap up, let me remind you there's a lucky draw where you can win awards, and there is also a separate session for AI and HPC users focused on E-Series with BeeGFS. My 2 key takeaways for this session would be that a complete data management portfolio is key to successful HPC and AI architecture. Netapp has that leading portfolio of on-premises and hybrid cloud, block, file, and object solutions for shared data management in both HPC and AI. The increased use of public cloud brings new challenges to public cloud and hybrid cloud implementations. But Netapp can help you not only store data, but also move it, optimize it, protect it, and secure it, and also optimize your compute workloads in the cloud. With this, I would like to thank you for your time, and please look us up on the web for additional information. Thank you.
Thank you, Mr. Petkovic. This was a very interesting talk. I like the ability that you presented of leveraging spot instances offered by cloud vendors as a means to lower the cost. Moving forward, we have a very interesting talk coming up by Mr. Rajesh Chhabra, Regional Sales Manager, HPC and AI-APAC at HPE. The title is Forecasting Next 5 Years, 2022 to 2027 in HPC. Mr. Chhabra, go ahead.
Thank you. Thank you for attending. I know there are lots of activities happening, and it's one of those things that when there's a lot going on, how do you choose which one to attend? Forecasting or trying to predict future is always hard. We have spent a lot of time in the industry, so we can make an attempt. Obviously, things like COVID today, right? Nobody knew 5 years ago or a few years ago that how things are going to pan out. But let me make an attempt and see how we go. So, the first thing that's going to happen, which is pretty much kind of sure, but is that we're going to have an exascale computer in 2022. So let me just show you this video, and you guys can all hear the, This video was created when we, in 2019, people in US and together with Cray came up with this idea that let's have an exascale day, and rightly so they chose October 18th, because 10 to the power 18 zeros, right, to get to an exaflop or exascale. And roughly at the time, we knew that we will be delivering an exaflop computer in 2021, it should go live in 2022. But as we all know, some of the things that are happening in 2022, which will continue to happen, is that we have had lots of COVID-related supply chain disruptions, right? So the biggest prediction of 2022 is actually these things are going to continue to happen, right? Unfortunately. Now, even when we were in 2020, when COVID came in, as we all know, COVID started in 2020, but the supply chain crunch came in 2021. Even at 2020, we did not really see the massive supply chain crunch that was going to come. We predicted a little bit of issues, but not to the extent of what's happening. And what will happen is that this will continue to be really bad for the 2022. And it's if someone says that they have not been affected, it's not true. Everyone has been affected, whether it's any company or any country. Everyone has been affected by this. But part of the effect is not just that, oh, there is COVID-related supply chain issues. There is also another thing happening that's creating this global chip shortage, and that is a huge IoT growth. The amount of chips requirement is just phenomenal now. It's grown crazy. All of you, who have started, and I'm sure you all did work from home, and your kids studied from home. Even if you bought maybe, let's say, an extra laptop or an extra device to sort of connect online and whatever during the last couple of years, it has all added into a lot of demand, and that's creating a huge global chip shortage, as we know. And there is this whole thing about digital twins as well, right? We have been hearing that, but what it is, there's just a huge demand. I have found this video as a very nice video to explain, what is digital twins. Most of you probably already know, but still a nice video to just have a look into what is digital twin. Live environment of a system. It could be anything, including people, right? You create a model, and you sort of monitor it live. But what it requires is lots of sensors, all sort of information gathering, analytics, and then trying to predict that what's happening. And this is happening literally for everything that we do. We used to first, let's say we want to create a building, we used to simulate, how things are going to happen, and then that's it, right? You finish there. But now there is like a live system maintenance, right? We also hear things like predictive maintenance and so on. By doing that, what we're doing is there is an active model that is being nurtured and used and monitored. And because of that, there's just a huge demand now of monitoring everything, buildings, your vehicles, and kind of any system that is out there. So yeah, very nice video showing what is digital twin and how it's being used. So these are all, this is all going to continue, as I said, in 2022. So let's touching sort of next year, what's going to happen next year, or the big things. And again, there are lots of things going to happen, but we are trying to sort of figure out or talk about things that probably matters to us folks in HPC, right? So the competition is going to intensify, and it's getting bigger and bigger next year. As we see, there are lots of new entrants in the market with lots of ASICs, right? You have, of course, various different CPUs coming, different GPUs coming as well, and just about I think I was reading something that there are some 50 startups in Silicon Valley today, doing new sort of specialized ASICs, which is basically new devices or new chips, right? So we're going to see a lot of this coming in next year. It's happening now even, but as I said, the competition is going to intensify next year. And then what will happen is when we have a mix of, devices, like today is kind of, you want to do AI, there is kind of a set thing that, okay, you have one type of vendor who's providing, your GPUs. But then when more vendors are able to provide things, you're going to need a platform which supports heterogeneity, right? You're going to need a heterogeneous GPU support, and not just GPUs, but basically all various different devices support, right? That's going to happen. AI adoption is going to continue to go. And there is a thing called swarm learning, and I have another video for that to show again what is swarm learning. And it's a concept developed in HPE. Well, there are lots of things happening, but we have a nice paper on this as well. And it's a blockchain-based platform. So it has a fantastic use case in healthcare and many places. But let me show the video first, and I can come back to this to talk about it. But let's see what is swarm learning.
Knowledge begins with observation. And although you may not have heard the term before, you've already seen a version of swarm learning in the world around you. Birds and fish often murmur or swarm, and as they do so, they are coordinating as a group without a centralized leader controlling the individuals. And if you imagine we are not looking at birds, but instead seeing intelligent devices operating in the real world, you begin to grasp why this adaptable system is so well suited for the future needs of autonomous vehicles and smart cities. In the current system, data is shuttled back and forth from the edge to a central data center for analysis and then deliver results to the edge. This back and forth method is slow, expensive, and not secure. It simply can't support the needs of intelligent devices. But with swarm learning, insights that are gathered by intelligent devices at the edge are shared globally without needing to shuttle private data to a centralized hub or cloud. Not only does this create a less expensive and more elegant system, but data sovereignty is protected. So how does swarm learning work? First, intelligent devices process data right at the source. This could take place within semi-autonomous vehicles that gather petabytes of driving data each day, or in a fraud detection system that tracks credit card purchases as they happen. In both these scenarios, the observations gathered at many locations are only truly valuable when they are shared and turned into a collective understanding by the entire group. This way, when one vehicle encounters a problem, an entire fleet can be trained on how to avoid it. This seems straightforward, but the act of shuttling data from locations at the edge to a central core introduces security threats. So, how do you make insights shareable but secure? This is why blockchain is also a necessary element of swarm learning. The blockchain network enables edge locations to share insights with each other in a trusted manner. And if a bad actor tries to infiltrate the swarm, the smart contract recognizes the imitator, protects the swarm, and prevents the unauthorized access. The result? Scientists, researchers, and AI engineers now train on much more data while following all privacy laws. And more data improves accuracy. This fosters better predictions, less bias, and quicker answers. It also saves on IT infrastructure costs by eliminating unnecessary data movement and duplication. The world is shifting from data centers to millions of centers of data. And as our planet grows ever more connected, swarm learning is helping us tackle some of our largest problems, from how to treat global health crises to distributing enough food to feed the world. This is just one way Hewlett Packard Enterprise is advancing the way people live and work. Learn how you can participate in the future today.
So, as I said, that different people are working on this. It's not just HPE working on this, but the whole idea is that we don't want to have, currently what we need to do is that, we collect data, we send it to somewhere central, and then we analyze that, and when we learn something from it, and then we have to push back the learning. The idea here is that you learn at the edge itself, and you only share the learnings instead of having to send the whole data. And that's why we mentioned about blockchains and so on. Blockchain-based data sharing or intelligence sharing is going to get more and more common from next year onwards. As I said, all of these trends are already happening, but how they're going to become more prevalent, and they're probably going to be more important in different times. And similarly, one of the things you may have come across another term called AIoT, and as it suggests, it's kind of the cross or the combination of IoT and AI, because obviously IoT so far been sort of kind of little dumb devices, collecting a lot of information to send it back. But when you actually put intelligence on those devices, it is the AIoT. So not just having a camera and capturing some information or just a feed, but actually being able to act on it right there, and then learning that, okay, what has happened, and just be able to share the knowledge. So that's
building a factory of the future.
Sorry, one more video, perhaps the last video. But this is just showing the AIoT kind of need. Sorry, continue.
That's where HPE GreenLake Cloud Services comes in, by bringing the cloud to you. Explore under its surface, and HPE GreenLake inspires some fluid thinking. Like, what if all your data, no matter where it's generated or stored, could work together seamlessly, enabling faster time to insights for your manufacturing operations, supply chain, products, and people. HPE GreenLake can bring the power of cloud analytics to your data. No need for a heavy lift and shift to the cloud. Pay as you go. Add services with a touch. And have it all managed for you. Skip the round trip to the cloud so you can make real-time decisions for your business. Wherever your data lives, now you can harness all its power to realize the promise of Industry 4.0 and beyond. Only with HPE GreenLake. HPE GreenLake Cloud Services. The cloud that comes to you.
So, as I mentioned that, as the AIoT explosion happens, more and more people need to have intelligent ways of capturing data and analyzing as well. And they may need something like what we have called GreenLake, where we can have kind of cloud on the edges or on your premises. And the reason I had this video just before one of the things that I'm about to talk is this, that in a couple of years now, what's starting to happen is that HPC as a service is going to get more and more common. People are going to, we know there's, some cloud sort of experience is going to grow, but at the same time, just the need of HPC as a service is going to grow. So more companies, and including government companies, will start to ask or have tenders where the entire thing, the entire HPC has to be provided as a service, which means, as you know, we all understand that as a service means that you pay per sort of pay per use, but also you pay periodically, and you have actually you care about the outcome instead of having to work too heavily on or providing part of the solutions. So, for example, even today, we have seen the government tenders will have they only ask for machines, right? Whereas they often go and try to sort of build their own data centers or own that and so on. Then we also see that sometimes, obviously, they subcontract DC separately, machine separately. But what I'm predicting and seeing that's going to happen is that it's going to be all together. even including the large institutions, they're going to say, okay, I want an HPC setup, and you figure out what's the DC requirement, how do you host this machine, and including the management of that. And that's where we have this thing called Green Lakes. And while, okay, yeah, this is a good example actually to share first. So we have a division in HPE called DC Technology Services. So what they can do is that they can come in, and they have done these projects where they'll work with the organizations to basically design the data centers. This is going to go a step further, I believe, in a couple of years' time, where they say, okay, you also figure out what data center, or it may be a colo, or maybe something else as well. And basically, they will be like, I'm giving you the responsibility of doing everything for me. And it was, very visionary, I think, on HPE's part, that when the CEO of HPE came in 2019, announced something like Green Lake, and boldly said that, okay, by 2022, whatever we do, everything that we do will be available as a service. And that includes everything that we do, right? We do HPC, we do AI, we do this and that. Today, you can pretty much buy anything from HPE as a service. Everything is available. And why I predict HPC taking a couple of years longer, HPC is always a bit more complex and sort of, it's still lagging in the sense of, while we can start to do things, but I think that it will become more common in another couple of years' time. And that's why I predict or think that it's going to take a couple of more years to have more and more HPC requirement as a service. Now we're starting to get a little bit further out, right? 2025. And what's going to happen? The biggest issue, biggest challenge, and it's kind of, 24, 25. We're going to start to have lots of cooling problems, okay? Because the new set of GPUs that are coming, they're crossing or touching 1,000 watts. So it's a kilowatt per device, right? Similarly, the CPUs are crossing the 500 watts limit. They are ranging, in 600 watts and so on, right? Some of this information is still very confidential, so we can't share a lot of details, but this is enough public domain knowledge where these things are happening. Why these things are happening? Number of cores are growing, right? We today have 64 cores, we're going to get to 128 and then 256, and things are heating up. Then we're going to have problems of trying to fit in more things, and there's the 3D stacking start to happen. So as a result, when there is a 3D stacking of a chip, you can only cool the top, and the cooling power is becoming more and more difficult. So what happens that you can't do air cooling anymore. The HPC centers are not going to have air cooling. Whatever is happening, it's all going to stop roughly around in another 2-3 years' time. If we see all the large centers that we have announced, or all the large projects we have announced in US since about 2018, they're all liquid cooled. The biggest supercomputer that is happening in Singapore now is the liquid cooled supercomputer. Similar stories in Australia or wherever we see. So this is going to become a lot more common and kind of the only way. There may be other ways, but like there are immersion coolings and different coolings. The point I'm trying to predict is that the air cooling is kind of dying for HPC centers. One other thing is going to happen, and we already have obviously ARM-based supercomputers, but they're going to grow. There will be more ARM-based technologies coming in the top 500s, and we will see that happening, right? So that's going to happen as well. Okay, now we're reaching the 5-year mark, which is very, very hard to predict. So 2026 and beyond, I think we will start to see more and more quantum computing. Now, I'm still a little bit skeptical in terms of when it is all practical, usable, and so on and so forth. So I have put really another few years out there when I think things will be happening. We have seen even in this conference that there have been lots of good tracks, lots of good presentations and talks. And there's a lot of work going on, but I do think it's going to take time, right? because currently the things are difficult, right? And if it is in the current form, that means if you still need those special DCs to host a quantum computer, then very likely it's going to be a service model, right? Because not everybody is going to be able to build these special DCs. They're going to have to just take the service. And I was listening to a talk yesterday where they predict that, okay, there will be some few quantum supercomputer centers, and they may even have to they will have to be combined with the HPC centers, and basically users use that as a service model, right? You have certain things or certain problems get solved in a quantum computer, but then they come back in the classical computers to try and continue to do the other thing that they're doing, right? As I mentioned, currently it's extremely sensitive to movement and temperature, so there will be other ways and newer ways also coming in. Now, so, and the cost. Remember, the cost is always a big thing. We have seen in the past lots of good technologies, but they disappear for one reason or the other if the cost is not right. And until the cost becomes good or practical, and only then it becomes a popular thing. So there's an Australian company, Quantum Brilliance, doing some really interesting work, having sort of like a quantum accelerator, kind of like a GPU or an extra device, right, which works with your CPUs and trying to do things at room temperature. I think this is going to be very interesting. And there may be many other things happening in this way. Similarly, there was another new technique that was just recently published from University of Melbourne, that there were ways to sort of do things cheaper using silicons, as more like standard things instead of what we're trying to do so far. So I believe that something along those lines is going to happen. It's hard to predict how exactly, but it has to be more practical in terms of building things and managing things when this becomes a reality. So if we try to sort of compare, right, some of the key events in the computing world was that, when we moved from those vacuum tubes to transistors, and that sort of had this, a single computer of, size of these rooms moved into the PCs, right? We saw that the big room size computers became PCs. Similarly, we saw then eventually the ICs came in, and we have all these super powerful chips, and now we have the computing power on the phone that we almost don't need PCs anymore, right? We are able to move around, and it has become so easy to have the kind of power that we have on our phones. So the next thing is quantum computing, whether we like it or not. And in fact, we like it, we want it, because we need more and more power. We always going to push the limits. It will happen for sure, and it'll happen eventually. It's the thing about what is that event that is going to make it happen. It has to be something practical. It has to be something that makes easy for this to do. So as I said, just like we moved from sort of horse carts to trains to airplanes, I think now we are ready to move into space travel. So all of these things are going to happen. It's a matter of like how it'll exactly come true. So I'm right on my dot, and if there are any questions, I don't know. Any questions from anyone? No? Okay. Thank you so much.
Thank you, Mr. Chhabra, for this, for your, HPE's forecast for the next 5 years. I have to say that I share your sentiment about quantum computers. They are coming, and they have their place in the quiver of the tools that we have to solve computational problems. Our next talk that has the title, "The Critical Role Open Source Storage Will Play in Advancing a Vision of Supercomputing for All," has two speakers. We have Mr. Joff Pearce, Solutions Architect at Softiron, and Mr. Andrew Howard, Associate Director, Cloud Services from NCI Australia. Please.
Hello and welcome to our discussion today, and thank you for the opportunity to speak at Supercompute Asia 2022 about this collaboration between Softiron and NCI and challenges for Supercompute for all. I really hope this stimulates some ideas that you could use in your organizations. First, I'll introduce Softiron and discuss some of the supercomputing for all challenges and how we believe Softiron can help in the storage space in this discussion. Although we can't solve every single problem, because this is more than just a product problem. And then Andrew will talk about the specific project that we've been working together on at NCI. So I'm Joff Pearce, a long-time technologist with a varied background ranging from programming through to enterprise architecture and lots of other things in between. So who are Softiron? Softiron creates world-leading task-specific data center solutions for the enterprise. We simplify and improve the data storage experience by enabling the easy adoption of enterprise-class open-sourced software-defined solutions at scale. Our product lines currently include storage, networking, and transcoding appliances, with more to come in the near future. While technically we're headquartered in the UK, we establish subsidiaries around the world, and there are more announcements to come in this region this year too. And you'll note that for quite a small organization at this point in time, we're spread globally, and that's not by accident. We're trying to maximize the skill level within our organization and minimize supply chain incidents on how we can deliver to our customers. So what are the factors that impact supercompute for all? So the IT industry has created a skills crisis in design and manufacturing due to the desire to keep costs as low as possible. We're trying to address these skill shortages, at least in Softiron, and we think that other organizations may well adopt our model as that we see the success with it. And when capturing data in the edge, in places where you simply don't control everything there's multiple dimensions for consideration in that. There's the security of the data, of course, and the lack of local skilled resource to manage that environment. We design and build all of our own products. We don't use third-party manufacturers. We track all physical software and hardware components and allow audit of our environments end-to-end if that's required. And we call this secure provenance. Nobody wants their data exfiltrated because of compromised hardware or software at the edge or in the data center. And so innovation needs to not just be at the product level, but clearly it also needs to be at the staffing level. And there's a huge amount of effort has to go into those staff because they're incredibly important to every operation. So you need regional skilled resources, which will lead to more and more innovation. By not concentrating on your storage, you can concentrate on those higher value tasks. So at Softiron, we build our storage appliances based on Ceph, which is an open source project. It's very, very versatile, delivers block, file, and object storage all from within a single cluster. It provides all those fantastic features that you're used to, like data replication, snapshots, storage tiering, and of course all with no licensing fees because this is open source software. I won't dwell on Ceph in detail because many of you may already know about it, but I'm happy to provide much more detail after this presentation. So as I mentioned earlier, Softiron is really trying to build resilience through our supply chain so we can deliver our solutions to our customers in a timely manner. As part of that initiative, we currently manufacture everything in California, but we're in the process of building a new factory in Sydney. And we expect to build more manufacturing around the world over time. Of course, we're not immune to global supply chain disruption, but we're trying to build an architecture and business model over time to minimize all of those types of challenges. And if we fast forward 5 to 10 years with a dozen or so manufacturing facilities across the globe, One affected facility might not affect the Softiron supply chain at all due to the ability to partner with local suppliers as other vendors other than ourselves start to lessen their reliance on individual geographies as well. Overall, the Softiron approach could lead to it could serve as a blueprint for the fundamental shift away from those centralized manufacturing countries that we see today. And with a shift to more edge facilities, hardware becomes more important as well because of the control, management, power consumption efficiency is also very, very important in all solutions at scale. In discussions with our customers, NCI and others, and other people at this conference this week, it's clear that skill shortages are real and that to have staff concentrating on storage, for example, is not where the high value tasks are for HPC and other types of organizations. You really want your staff to be fulfilling those high value tasks. So that's why at Softiron we designed and built hyperdrive specifically for Ceph, for a platform that's resilient and in many cases is self-healing, which allows you to set and forget our storage, allowing you to concentrate on those higher value tasks. So with a lot of focus, of course, moving to things like exascale compute, resilient storage can become very valuable. The lack of vendor lock-in that we provide also helps with solution resilience. And as challenges come along to address exascale compute, you don't want that focus to solely stay on storage. You want to focus on the challenges that you're going to need in the compute space. So Softiron's developed user interface and hardware specifically for Ceph to minimize all of the challenges that come along with open source. So with more data being captured and stored at the edge, an architecture that enables remote management is absolutely critical. So management means control of the entire stack, so from hardware, operating system, through to the software as much as possible, with integrated as much as possible too, to minimize the local skills at the edge required to operate a solution. So we believe a solution with secure provenance, so that security through the hardware, software, operating system, etc., is absolutely critical to provide the assurance that your data is safe in your edge locations where you capture your data. So we think we've got a better way of building software-defined infrastructure. Traditional vendors, traditional proprietary vendors will, of course, give high cost but great performance and capacity. You can roll your own, of course, which means that you will get a large degree of complexity, but a lower cost and variable results on performance depending on the skill levels of your organization. So we deliver a proprietary storage solution outcome at a much lower price. Full support and we provide full support from hardware through to software, and the solution is delivered pre-configured to all of your requirements in your edge or data center locations. So it takes more than a hot storage product to deliver these things. We have open source at our core, which means there's no vendor locking to us. If you decide you want to change tack and do one of those other approaches, you could. But we believe our products offer that simplicity that you won't want to move away. But it also gives you modern storage services and parallel scalability. The task-specific appliances that we build mean that we have low complexity of management, low power, and therefore low heat with optimal resilience and high performance. In fact, these systems have been designed from the ground up just to run Ceph, which is unique in the industry. Not even other appliance vendors can claim that because they use contract manufacturers and reference designs from their vendors to build their products. the fact that we own the design and manufacture of our products means we don't do that wherever feasible. And as a result, we could do some pretty out-of-the-box things. So we use CPU just right size for doing Ceph throughput, not for doing general compute tasks, which we don't need to do. And therefore, that means that we get very low power usage and therefore low heat output. And in addition to that, we take a platform approach to manufacturing, which enables us to achieve the economies of scale that the big guys do, at the same time build our manufacturing capacity in a modular and resilient way by distributing it globally. So I'll just quickly run through these slides to demonstrate some of the power and heat savings. Feel free to have a look at these online in more detail, but you can see from these heat signatures that we produce an awful lot less power than equivalent boxes running Ceph as well. And therefore this can be delivered anywhere, whether that be at the edge or in the data center. And that drives sustainable solutions and the ability to deliver those solutions anywhere. If your data capture location happens to be a broom closet in a partner's office somewhere out in the ether, that's okay. We can work on two-phase power, single-phase power, and works perfectly in those types of environments and is safe and secure. So Softiron is investing significantly in this region. As I already mentioned, we're already building a factory in Sydney, Australia, and expect to hear more announcements later this year for further investment in this region as we roll out our logistics and manufacturing processes throughout the world. And then finally on me, before I hand over to Andrew, here's some screenshots to give you a flavor of the simplicity of our Softiron manager. For those of you familiar with Ceph, you'll see that some of the information displayed here is quite hard to do if you don't control the hardware. And as I've already said a few times, we control the entire stack end to end and can do some interesting and very things that make life much simpler when using Ceph. And we also have other things that nobody else can do, like the Ceph button, which in the event that a hard drive or other drive fails, you can press the Ceph button, tell Ceph that drives are being temporarily removed from the system, replace a failed drive, place it back inside the system, press the red Ceph button again, and those drives are now available for I/O throughout the entire cluster. So that's my overview of Softiron and why we have designed and built the Ceph platform the way we've built it. And now it's over to Andrew to discuss the specifics of the project implementation at NCI. I'll welcome Andrew to the stage. Thank you.
Thanks, Joff, and thanks, everyone. I'm Andrew Howard, Associate Director Cloud Services at the National Computational Infrastructure in Canberra. We see some of the issues very similarly to Softiron. Having local investment in the Asia Pacific region is extremely important for us. We are also looking at, sorry, where's my slides gone? Where have we gone? Yeah, pushing that. Okay. Where's the rest of them, Joff? Okay. Sorry, well, I'll just talk while we have some technical difficulties. As Joff mentioned, HPC at the edge is something really critical for us. It's something we all face in terms of the deluge of data that we're seeing. As Joff mentioned, the kind of 75% external data. For many HPC facilities, that's a lot higher. We consolidate data sets from many external sources, and having the capability to have a service that is able to work across our maintenance windows is also very important. Once we get the slides up, you'll see how NCI have integrated Softiron as both an edge and an internal processing solution for many of our needs. Joff mentioned the hardware provenance. That is also extremely important to us. Having local manufacturing in Australia is something absolutely critical. Our manufacturing base has diminished over the last couple of decades. And in these days of COVID, we have been significantly impacted by supply chain issues. Local manufacturing gives us a level of assurance that the vendor will be able to meet our needs on an ongoing basis. Something that we find really attractive with Ceph is the capability to dynamically configure the system to support both replication for extremely rapid I/O capabilities, but also using erasure coding as a way of extending the storage availability for projects which need reliable, resilient data services, but may not need full performance. So let's move on. NCI operates quite differently from a number of other HPC facilities. We closely couple our HPC and storage and cloud services. This differs from a number of other HPC facilities where the amount of storage connected to the HPC system is quite limited, but there are large pools of external storage. This requires a processing workflow where data is staged into the HPC system, processing performed on it, and then the resulting data is transferred or staged back out into the storage. NCI has the advantage that the storage is extremely close to our HPC facility. We also differ quite significantly by having our cloud services also tightly integrated into our data environment. Our primary HPC storage is Lustre, which provides extremely high-performant parallel I/O operations. While this is extremely important in some circumstances, we also hold a significant number of both national, regional, and global datasets which our users need to compute against. We've selected Softiron as an intermediate tier in this processing. Many of our data products are delivered via a cloud-based service. Storing, though, that primarily static data on Lustre is extremely expensive, and that Lustre storage could be used more effectively for HPC workloads. So we'll be transferring a large number of our data collections over onto the Softiron capability that we've purchased, which is around 12.5 terabytes. Because it provides us a flexible mechanism of supporting different protocols for different operations and performance in our organization. We've also had a growing demand for S3 access, both for traditional object-based storage and for our data collection storage. So we see the use of Ceph and particularly Softiron in this role, providing us a great number of advantages. We have multiple Lustre-based file systems, as I just mentioned, which are connected over 200 gig Infiniband. They're really suited for highly parallel read and write operations within HPC applications. We also run a triple site tape backup facility where 2 of the tape copies are kept on ANU campus, and the 3rd copy is kept about 15 to 16 kilometres away to deal with a catastrophic natural disaster. Australia is well known for these, and currently we are evacuating about 500,000 people out of Sydney. We also need to maintain a cold storage copy, which we also store off-site at the tertiary data centre. And we use NFS currently front-ended onto Lustre to support our data collections catalogue. Moving these directly onto Softiron and an S3-based object store removes a lot of the intermediate data transfer capability and inefficient power requirements to actually pull data off Lustre and serve it out via a web-based interface. We have an existing investment of around 6 petabytes of Ceph, which we've built our own. This is connected to our Nirin cloud, which we use for block, volume, and Ceph-FS capabilities. We've traditionally built our own Ceph, which leaves us in the position that we have no support. If something goes wrong or if we make an incorrect design choice, all of the cost is on us to correct it. And if something goes wrong, we really don't have anyone we can reach out to. Of course, open source communities are great, but everyone's configuration is typically unique. The cost of hardware and software maintenance is also quite significant for us. Having the capabilities that Softiron does, with particularly the Ceph button, really reduce our total cost of ownership and allows us to utilize our data center operations team to actually perform hardware maintenance. Over the last 2 years, this has also become increasingly vital. Australia, in response to the COVID pandemic, effected extremely tight lockdowns at a city, state, national level. And for many years, we were only able to have a very limited number of people able to access the data centers. So having a very easy to use, a very easy to maintain capability, which Softiron provides, is a great advantage to us. We also typically will have quite complex bespoke configurations based on 10 years of doing things with Ceph, which also imposes a significant engineering cost on our cloud services teams. So we're looking for a number of solutions to these problems: how to reduce our total cost of ownership, how to actually provide a support model and capability where we have someone to be able to ask questions to, having a local manufacturer where if we do need replacement components, it's about 3 hours by road away rather than having to wait a minimum of 24 hours for any product to arrive from international. That has also been a significant impact over COVID, where our borders have been closed pretty much completely for the last 2 years. Modular expandability is also something that was really attractive to us. We're able to start with the 12.5 petabyte investment and then dynamically grow that by just adding additional storage modules to the existing Ceph cluster with no downtime at all. Softiron provides a very nice graphical user interface which simplifies all of these functions and operations. Low power is an essential thing for all of us in the HPC community. We're always trying to balance the cost of energy and, of course, the counter cost of cooling to remove the heat that energy generates. Utilizing an ARM-based platform, which is designed for purpose for Ceph, with around 25% of the power requirements of an x86 platform, allows us to dedicate that power to other HPC facilities. Reducing our senior engineering time requirements has also been critical. As I mentioned, we haven't been able to get our staff to be able to touch the hardware. So anything we can do to reduce that and to lower the barrier is really, really useful for us. So where does Softiron fit into NCI's existing storage portfolio? We see this as a new tier or a new capacity of storage, supporting our object-based applications, both in our cloud and HPC environments. This will have this also allows us to have a dual visibility of both objects and POSIX to support some of our quite older workloads and provide us a really effective way of starting to employ object-based storage on an ongoing basis. This is also not part of our existing storage allocation. NCI, I would expect, like most of you, has a never-ending demand and an increasing demand for storage. This is typically allocated on a yearly cycle, so having around 12.5 petabytes of effectively available storage allows us to do things like reprocess 4 to 5 petabytes of data streamed off our tape libraries in a way that is highly performant, which we need to do on some occasions, particularly in terms of satellite data sets, where we may receive the initial satellite data and then need to perform further post-processing of geo-rectification or cloud removal. And the Softiron platform is really great for doing that. The flexibility and ability to be partitioned depending on our workloads and requirements is also a really attractive value proposition for us. The capability for automated data replication between NCI on the east coast of Australia and our sister supercomputer centre, Pawsey, on the west coast of Australia, also allows us to provide eventual consistency of data sets. By doing it this way, our users don't have to worry about data transfer tools. They're able to upload the data into a shared area and know that that data will be replicated in a very network efficient manner to our sister site, where they're able to continue processing on it. So, as I mentioned, we want to create a more effective storage tier. We really want to reduce the cost of storage for primarily static collections, but we have certainly the capability of read-write operations and for non-static collections as well. The Softiron service will be plugged in at 100 gig into our facility 100 gig Ethernet service, and the capability for immutability of data also is extremely important for things like genome sequences, where we need to ensure that there has been no corruption or modification to the data, particularly in the human genome space. As I mentioned, we see this as a really good vehicle for reprocessing tape-based data sets, and to also provide a storage tier for our users who have an application which will use a fairly large tape data storage facility, but need faster access for a short-term task. It will serve both HPC, cloud, and our edge-based data transfer capabilities. Softiron has been working with NCI for around a year, where we initially did a proof of concept, and we're building a Ceph Centre of Excellence between Softiron and NCI, where Softiron have been kind enough to leave a completely operational Softiron stack, which is outside our 12.5 petabyte purchase. This will be available for people who wish to test Softiron, see how it works. We'll have a mini Openstack cloud connected to it, which will allow multiple I/O operations, multi-client, a distribution capability. We're also planning on plugging Kubernetes into that to facilitate evolving container-based workloads. The multitude of access interfaces, block, volume, S3, also makes things a lot easier in our context. We can configure this service as we need it, when we need it, dynamically and flexibly. So if you'd like more information on NCI or what we're doing, please contact me. Joff is Softiron solution architect and is the expert on everything Softiron and a lot of things Ceph that we didn't know. So I'd really encourage you to reach out to Joff if you do have any Softiron questions. He'll be more than happy to help you. So that pretty much concludes our presentation. Just let me check I haven't missed anything. I think that covers it all. Does anyone have any questions before we finish off today? Joff, did you have any other things that we'd like to talk through? So one of the questions is how we actually move the data in and out of our facility. We typically have a number of edge nodes on our HPC facility called copy queue nodes. Because you can't access outside of the HPC within an HPC job, having 100 gig access allows a user to queue a copy queue job to stage data into an HPC environment. And we're also looking at mechanisms of integrating object-based access directly from our HPC, but doing that at a higher level in the operating system using S3 CMD or rclone as a mechanism of dynamically accessing S3. We've also explored fuse-based access, but have found that slightly memory intensive in our HPC environment, where it's really essential that we keep the operating system footprint as small as possible to provide as much memory for the applications that our users really want to run. So, no more questions. We'd really like to thank Softiron for their long-term involvement with us, setting up Australian manufacturing, and providing us a solution that will meet our needs, hopefully for the next decade or longer. Thank you very much, everyone.
Thank you, Joff and Andrew. Let me emphasize the point that both speakers were trying to make. The ability to be able to trace the provenance of your software and hardware is important now more than ever. As if you recall, a few years ago, both AWS and even Apple had this major problem when it was speculated that there was some firmware backdoor in some of their hardware equipment, right? And it was really hard to prove whether this backdoor really exists or not. However, with Softiron's solution, I feel you are able to mitigate this, and this is really, really great in this day and age. So thank you for that. Moving forward to the last talk for this, before we take a short break, we have Mr. Sooyoung Moon, HPC AI Senior Specialist at Microsoft. And the title of his talk is A Simple Way to Run Large-Scale Training on Azure HPC AI. Mr. Sooyoung Moon, please.
Hi, thank you for your attention to Microsoft solution for HPC and AI. I'm Naoyuki Sogai, who is leading an Asia-wide team for HPC and AI solution at Microsoft, and will be sharing with you today an overview on a simple way to run large-scale training along with my team member Sooyoung. With assuming that many of you already have rich experiences of running HPC and AI workloads in on-premise cluster environments, you might have concerns or feel challenges like this with taking advantages of cloud. As HPC and AI workloads are very special and diverse per project by project, these points like scalability, agility, extensibility, trustworthiness, and versatile capabilities are all important. Then, while acknowledging these could be challenges with cloud in general, are these really challenges for Azure HPC and AI specifically? Actually, we don't believe so. Back in December 2021, there was the latest round of MLPerf training benchmarks, which wide variety of HPC and AI infrastructure providers joined across on-premise and cloud. Microsoft Azure joined that and showed such a strong result, delivering the #1 performance by a cloud provider, and #2 even over all providers, including on-premise. And even before that, in November 2021, Azure was even ranked at the 10th among the world's top 100 supercomputers at the first ever achievement as a public cloud. These accomplishments to have proven the massive scalability of Azure HPC and AI were made by an offering to run NVIDIA A100 with 80 GB memory and Infiniband on Azure, which is publicly available for everyone, including yourself. What makes Azure such a market-leading HPC and AI solution is its comprehensive design approach combining the best of supercomputing and cloud. We support a smooth path from your baseline for HPC and AI workflow across compute, networking, storage, orchestration, and intelligence services, so you can use the same trusted tools and processes to work with your overall HPC AI workloads. Azure HPC and AI Cloud is built to fit your workloads, including tightly coupled workloads, using the latest CPUs from Intel and AMD, as well as advanced GPUs like NVIDIA A100, all backed by low-latency, high-bandwidth Infiniband interconnect, along with high-performing storage like Netapp and Lustre. All those Azure HPC and AI capabilities are optimized to meet your simulation and modeling needs in an agile manner through intuitive user experiences for orchestrations across clusters and jobs, in combination with a wide variety of market-leading schedulers and tools from third parties. For AI workloads, the benefit of Azure HPC and AI can be enjoyed not only by using its GPUs directly, but also leveraged through the close partnership between OpenAI and Microsoft, working towards the next generation of very large AI model, as well as innovative Microsoft research projects like DeepSpeed, for notable examples. Also, we have an offering called Azure Machine Learning to provide intuitive experiences for AI/ML workloads. Last but not least, these Azure HPC and AI capabilities are well designed to work seamlessly with your on-premise environment by hybrid configurations, so you can utilize it with flexible controls on data and network, just like an extension to what you have been using. With that, I would like to hand over to my team member Sooyoung to walk you through how effectively and efficiently you can take advantage of such Azure HPC and AI capabilities for your large-scale training workload.
Hello everyone, I'm Sooyoung Moon, Senior HPC Specialist of Global Black Belt team at Microsoft. Today, let me share how easily you can run large-scale machine learning on Azure without a significant amount of your time and efforts. Usually, large-scale machine learning requires customized containers with a specific model inside, an input or checkpoint data set on top of GPU instances. However, setting up the host virtual machine for optimal machine learning environment from scratch is not an easy task for most of AI and machine learning developers and users. So, to help you quickly get an optimal environment, Azure provides powerful GPU instances like NDV4 and NDMV4, as well as customized virtual machine images for HPC and AI, intensively tested and optimized by Microsoft. NDV4 topology file is one of the most important components to get the best nickel performance on NDV4 or NDMV4 instance. Slum is one of the most popular open source job schedulers, and NVIDIA Inut simplifies Docker container interface for distributed architecture. And NVIDIA Pixis plugin for Slum invokes containers with Inut. PMIX enables MPI applications to run from the containers by Slum commands, and Nickel RDMA Shop plugin plays an important role to accelerate RDMA over InfiniBand communication. You can also take advantage of proven container images available from public or commercial repositories like NVIDIA NGC. For example, NGC PyTorch provides commonly required software for AI and machine learning, including Python, PyTorch, CUDA, Nickel, OpenMPI, and so on for your convenience. This is a reference architecture of HPC cluster for distributed machine learning on Azure with the latest GPU instances and NFS services to share user data across the cluster, as well as a user-friendly job management interface of popular schedulers like Slum. The NDV4 or NDMV4 instance is based on NVIDIA's latest A100 GPUs. And one thing special in this architecture is that Azure is the only public cloud to support InfiniBand network for internode communication, even with 200 gigabps bandwidth per GPU or 1.6 terabps per VM, which enables large-scale machine learning jobs to scale up to hundreds of virtual machines or thousands of GPUs without significant performance degradation. And optionally in this architecture, you can also include a managed DB instance for Slum job accounting and Azure Native File Service for high-performance I/O with support for dynamic resizing, with which you can optimize the high-performance storage costs. From the networking point of view, we recommend you to use separate subnets according to the role of virtual machines and services to avoid any interference between them. In addition, an orchestral solution named Azure Cycle Cloud running on a separate VM integrates job scheduling with VM provisioning, which makes auto-scaling of the cluster possible according to the number of VMs or number of GPUs requested by user jobs without any intervention by IT administrator. Another benefit of using CycleCloud is you can define and create clusters with templates, so can minimize the lead times and unwanted human errors across similar deployments. The blob storage represented on the right at the top is used to save and access CycleCloud project files and other types of files to be downloaded onto the cluster for further customization. From job flow perspectives, It's almost exactly the same as what you would see and feel with the job schedulers for the on-prem clusters you might have today. When a job is submitted by a user, Slum forwards the request for GPUs or virtual machines to SycleCloud, and then SycleCloud creates virtual machines if needed according to the resource requirements. Once enough VMs are ready, Slum dispatches the job to the allocated virtual machines and also starts container instances from a custom image with the input data set mounted from the shared storage. Finally, the job starts running from the containers with internode communication using optimized MPI and or Nickel libraries enabled over Infiniband network. Under the hood, Pearce's plugin loads the containers via Slum, and PMIX enables MPI communication between containers. However, PMIX is not a mandatory plugin if we are not using MPI from containers, while Pearce's is to load the containers from Slum. You may think deploying an optimized HPC cluster on cloud should be extremely challenging, unless you are an experienced HPC and AI user or administrator with deep knowledge of cluster managers, job schedulers, and the specific cloud platform you are using. However, it's not true with Azure HPC and AI. According to my real experiences of enabling HPC and AI customers and partners, I can say you will be able to create a working cluster for large-scale machine learning on Azure without huge investment of time and efforts. I'm sure many of you can do it in a very short time, even in an hour, as far as you have a web browser connected to the internet and very basic knowledge of Linux and Azure. SycleCloud helps you. You can just follow the steps described here and don't need to worry about the OS level commands or scripts, as SycleCloud automatically executes them for you behind the scenes. I'm not doing a demo today, but can share some screenshots of important stages already described in the previous page. As you may feel from these screenshots, you can use web interfaces most of the time while you are configuring the environment, including creating virtual networks and subnets, setting up the SycleCloud, creating a managed DB instance for Slum job accounting, and starting and stopping the cluster. The first screenshot shows the virtual network and the subnets as described in the configuration diagram in previous page. And the second screenshot shows an example SycleCloud UI with a custom Slum template with which you can easily create a cluster for distributed machine learning with containers. The third one shows the DB instances created for the job accounting. And then screenshot 4 shows the status of the scheduler node when you start the cluster. So only the scheduler node is created when you start the cluster, and the compute nodes are created later only when you submit a job. Screenshot 5 shows the remote terminal screen where you can run Linux commands to prepare and submit Slum scripts to run the machine learning jobs. Please note I used the Nickel benchmark script in this stage rather than a real machine learning job script, as I just wanted to show how long it takes to start the GPU cluster when a job is submitted. The screenshot 6 shows the final stage of the deployment with all the compute nodes start running, and the machine learning jobs have started according to the Slum job script. So you can manage the cluster provisioning and job handling from the Cycle Cloud UI most of the time, and some basic Linux commands from the command terminal. And Cycle Cloud UI also provides additional information of the cluster, including real-time history of the number of live instances and important events in provisioning processes as shown in screenshot 6. In order to run distributed machine learning jobs with Slum, you need to make sure to find all of the required environment variables in the job script for optimal use of GPUs and Infiniband on Azure, as well as proper Slum options to request compute resources and set up the container environment correctly. Be careful to set the number of nodes, the number of tasks per node, and the number of GPUs per node to meet your requirements correctly. If you are already familiar with the Slum scheduler, it'll be very easy for you to customize the script for Azure with some recommended variables added. If not, you can just refer to the link at the bottom for example job scripts to run some benchmarks using Slum and containers. At least, please make sure to specify Nickel topo5 with an appropriate path to the NDV4 topology file to get the Nickel performance as expected. You need to define it in the Slum JavaScript body to optimize Nickel performance on the VMs, but need to include it in the bash command argument to use it from the containers. There are several machine learning use cases with samples and manuals available from the internet. NVIDIA also provides example models implemented with various frameworks, and BERT PyTorch is one of them you can download from GitHub for free. The steps shown here is for pre-training of BERT model with Wikipedia corpus, and the diagram in the blue box describes the overall procedure with the key Azure HPC and AI components and the model codes and dataset as well. You start with choosing NDV4 or NDMV4 instances and Ubuntu HPC virtual machine image, then configure a cluster with the Cycle Cloud, and then finally set up BERT and run the training job. If you want to try it yourself, please make sure to do that with a stable internet connection, as it takes about 15 hours to download the pre-training dataset. More details on how to set up the example environment and run the training jobs are available from the link at the bottom. These are screenshots from one of my hands-on labs with BERT. Once the Slum job starts, you will see Slum logs Pixis plugin loading containers successfully, Infiniband topology mapping, and liquid environment settings, and also see the iteration number steadily increases up to the predefined limit. You can also get some insights on the expected completion time or performance of the particular model by referring to the elapsed time per iteration, even before the whole job finishes, normally in a very long period of time, like in days or even weeks. As Naoki-san previously mentioned in his presentation, Azure NDM v4 cluster has achieved the highest MLPerf training performance on cloud and the number 2 performance overall as of December 2021. From the published details available from the link at the bottom, you can see Azure NDM v4 consistently shows good performance across various machine learning categories, sometimes better than and sometimes comparable to the on-prem systems. Again, this is possible with the latest NVIDIA A100 GPUs on ND v4 and NDM-v4 and one-to-one non-blocking InfiniBand interconnect, and the optimal software environment with Azure HPC and AI virtual machine images and Scikit-Cloud Orchestrator. The ML Commons webpage provides all the details of the benchmark scenarios and base rules to run them for fair comparison of performance of different architectures and implementations. There are many sources of information about Azure HPC and AI, and here are some important references that you might be interested in. Some of them are for your hands-on practices, and some of them are for Microsoft's strategies to support AI and machine learning, and some of them are about significant achievements Microsoft has already made so far. Also, please use the link at the bottom to contact Microsoft for further information or to share your feedback on Azure HPC and AI. A Microsoft representative or a partner will get in touch with you according to your kind input. Finally, I hope you enjoy the Supercomputing Asia event to the end and hopefully have a good opportunity to collaborate with Microsoft for HPC and AI. Thank you very much for your time.
Thank you, Mr. Moon. It's great to see that Azure Cloud can be used for HPC and AI thanks to the InfiniBand capabilities. So we are running slightly behind schedule, and I suggest we just take a short 5-minute break and we reconvene in 5 minutes, so that will be at 4 p.m. and we continue with the last stretch of the industry track. See you soon. Thank you.